Thank you very much, and thanks everybody for attending. What I want to talk about this afternoon, excuse me, is why adolescents take risks, and to try to give you some answers to that question that are derived from research on both behavioral science and neuroscience. So let me go ahead here. Hold on a sec. Sorry. There. So let me put this in a public health context. That if we look at adolescence as a period of life, in general, it's a very healthy time in development. There's very little illness or disease. And the major contributors to morbidity and mortality during adolescence are behavioral in nature. Some of these will be very familiar to you. So if we look at data comparing adolescents to adults, we see that adolescents commit more crimes. This is a figure that's referred to as the age crime curve. It is very robust over time and across industrialized nations. And what it shows you is that the rate of crime increases from pre-adolescence into adolescence, peaks around age 18, and then declines after that. As I said, this is a pattern that has been seen across many countries and across historical time, and it's true for property crime as well as violent crime, as you see in this slide too. Again, showing the peak in crime during the late adolescent years. But crime is not the only risky behavior that peaks during adolescence. One that is a surprise to most people is that adolescents compared to adults drown more often. And that's, I think, interesting because we think of adolescents generally as being stronger and having more endurance than adults. But these are data from the CDC on unintentional drownings, showing again that they peak during the late adolescent years around the same time as crime. And I think it's reasonable to suspect that this peak in drownings at this point in time is not due to weakness, but rather due to reckless decision-making. Adolescents also attempt suicide more often than adults do. Adults, as you probably know, more often complete suicide, but suicide attempts are much higher during adolescence as well. These are also data from the Centers for Disease Control and Prevention on non-fatal self-inflicted injuries, again showing a dramatic increase from pre-adolescence into adolescence and a peak sometime in the mid to late adolescent years. I could show you many, many other examples of similar patterns, but what we see across many, many different types of risky and reckless decisions that this increases from pre-adolescence into adolescence and then peaks and then declines. So for many, many years, psychologists have been trying to understand why this is, and a number of different theories about adolescent risk-taking have been advanced. But one popular one is that adolescents are illogical. But if you look at data on logical reasoning abilities, what you see is that these abilities increase steadily from childhood into mid-adolescence, reaching a peak at around age 15 or 16, and then not declining after that. So at least by the time adolescents are in this heightened stage of risk-taking, they're no less logical than adults are. It has also been thought for a while that perhaps adolescents underestimate risk. That is, they engage in risky behaviors because they're not cognizant of the dangers of engaging in them. And that turns out not to be true. If you give adolescents and adults surveys asking them to estimate different types of risks that could result from various behaviors, what you find is that adolescents actually overestimate risk, and they do so even more than adults do. Many adolescent textbooks describe adolescents as suffering from delusions of invulnerability. But what research shows on this is that although adolescents do suffer from these kinds of delusions, so do adults. And the rate of belief in invulnerability is no higher during adolescence than it is during adulthood. It had been thought for a while that maybe adolescents simply think poorly when making decisions. That is, not that they make bad decisions, but that they make decisions badly. But studies of information processing and basic cognitive abilities show that, as is the case for logical reasoning, information processing abilities increase throughout pre-adolescence and early adolescence. And by the time people are 15 or 16, they think just as well as adults do. And then finally, Some people have speculated that perhaps adolescents are just unaware of the dangers associated with risky behavior. That's a little hard to believe given how much time and money we spend in schools teaching adolescents about the dangers of various risky behaviors. And in fact, surveys show that adolescents are very much aware of the dangers associated with various risks like driving after drinking or having unprotected sex, but they engage in those behaviors anyway. So psychology, I think, has come up short in explaining these age differences in risk-taking. If you look at many different aspects of cognitive development and combine them together, these are from a study of ours that I'll tell you about as the talk goes on. What you see here is that basic cognitive abilities increase from about age 10 till about age 16 and then plateau then. And so that it's safe to say that adolescents really are as smart as adults by the time they turn 15 or 16. So the question that we've been asking, and it's a question I think that a lot of parents ask as well, is if adolescents are so smart, why do they do such stupid things? And I think part of the answer can be found by looking at the developmental trajectory of psychosocial capacities like impulse control or resistance to peer influence or risk perception. And what we see here is that these capabilities continue to mature from early adolescence on and continue growing into the mid to late 20s. And so it's safe to say, I think, that adolescents are intellectually mature before they are socially and emotionally mature. So given this, my colleagues and I have proposed an alternative view of adolescent risk-taking. And that starts from the idea that heightened risk-taking in adolescence is not due to cognitive deficits, and that it is, in fact, the product of psychosocial rather than intellectual immaturity. We think that risk-taking in adolescence is normative, that it's evolutionarily adaptive, and that when we evolved as a species, adolescence was a time during which it was important for people to be willing to take risks in order to reproduce. So for those of you not familiar with adolescence in other species, all mammals, as you know, go through puberty. And so we can use other animal models to learn about human adolescence. And at puberty, in most other species, the juvenile leaves the natal environment and goes out seeking other mates. And this is very risky behavior because there are competitors for this as well as predators. And so if adolescents didn't engage in risk-taking, they wouldn't reproduce. And it turns out that if you look at the age at which females are most likely to produce the largest number of offspring by becoming sexually active, the age at peak fecundity among females is about 5 years after they have their first period, or 5 years post-menarche. And in industrialized countries today, menarche occurs at around age 12. So 5 years beyond that is around 17, which is coincident with the age at which we see the peak in risk-taking in most industrialized societies. So the two may have something to do with each other. So we have tried to frame this understanding of adolescent risk-taking within the advances that have been made in developmental neuroscience over the last 10 to 15 years. And we have proposed what we call a dual systems model of adolescent risk-taking, referring to two different brain systems. So one brain system is what we refer to as an incentive processing system. This system links to certain nodes of the brain. The ventral striatum, which includes the nucleus accumbens, as well as the orbitofrontal cortex, are the primary loci of this. This is a system that's important in how we evaluate and predict potential rewards and punishments. It also turns out to be very important in how we process emotional and social information. So what do we know about how this system develops and changes during adolescence? Research shows that this brain system undergoes major changes in early and mid-adolescence around the time of puberty. Some of the changes seem to be directly related to the impact of sex hormones on the brain, but others occur at the same time as puberty because of genetic programming that links them up together. And most important is an increase in brain activity involving the neurotransmitter dopamine in pathways that connect the limbic system, that's where the ventral striatum is, to the prefrontal cortex. Dopamine, as most of you probably know, is a very important neurotransmitter for learning and especially for the experience of reward or pleasure. And some people joke that when we anticipate something very pleasant happening, like food or sex or money, we get a little dopamine squirt in the brain, and that's what makes us feel excited and looking forward to the pleasant experience, the rewarding experience. What we see if we map out dopaminergic activity in this pathway over time is that it shows an upside-down U-shaped pattern with age. So dopamine activity in this region of the brain increases pre-pubertally through puberty and then peaks at around mid-adolescence and then declines as people move into adulthood. And these changes in dopamine activity have some behavioral consequences downstream. They make us more attentive to rewards, because if rewarding things feel good, we will be on the lookout for them more vigilantly. They lead to increases in sensation seeking because we are more willing to pursue exciting and novel experiences, even if they're perhaps a little bit scary, in order to get the dopamine squirt. It makes us more easily emotionally aroused. And it also increases our attentiveness to social information, especially during a period of life in which social relationships are so very, very important. Now, I mentioned that our model revolves around two different brain systems. So this first one is the incentive processing system. A second is a system that we refer to as a cognitive control system. And this is a brain system that's important for executive function. So it's important for things like working memory and logical reasoning, planning, and regulating impulses. And this system is localized mainly in the lateral prefrontal cortex and the anterior cingulate, as well as the posterior parietal cortices. Now, the cognitive control system also changes during adolescence, but it matures along a different timetable than the incentive processing system. So the cognitive control system develops gradually from pre-adolescence on, and it continues developing well into the mid-20s, and it's largely independent of pubertal maturation. So it's very, very different from the incentive processing system. And we have mapped out some of the important changes in brain anatomy, that is the structural changes in the brain that occur that go along with this, with the changes in cognitive control. And these are seen in synaptic pruning, that is the elimination of unnecessary neural connections, as well as myelination, as the growth of white matter that surrounds axons in the frontal and parietal lobes, but also in increased and improved connectivity within cortical regions of the brain, but also between cortical and subcortical regions, and importantly, between the limbic system and the cortex. And these changes result in better impulse control, better coordination of emotion and cognition, and more foresight and planning ahead. But as I mentioned a moment ago, the timetable for the development of this system is very different than the development of the incentive processing system. And it's this difference in timing that helps us understand risk-taking during adolescence. Because the excitation and arousal of the incentive processing system occurs early in adolescence, around the time of puberty. But the maturation of cognitive control is gradual, and it's not complete until late adolescence or early adulthood. Some people have referred to this as a maturational imbalance. And a metaphor that we use to describe this is that the brain's accelerator, that incentive processing system, is activated before a good braking system is in place. So with that as kind of a theoretical conceptual background for our research, let me pause and give you a brief summary of this, as well as present some hypotheses that we're going to test with some data. So an important part of this framework is that reward-seeking and self-regulation are subserved by different brain systems and develop along different timetables. The literature on adolescent risk-taking and decision-making often confuses sensation-seeking and impulsivity, and they're not the same thing. To do a little thought experiment here, I want you to imagine people waiting in line for a long time to ride a roller coaster. So they're engaging in sensation-seeking, that is, they're interested in this novel and exciting experience, but they're showing very, very good self-regulation or impulse control by being willing to wait online for it. So they're really two different things that need to be measured separately. And that these systems mature along different timetables, and so it makes middle adolescence an especially vulnerable period for risky behavior, because that's the time when the imbalance is the greatest. And we also believe that this vulnerability caused by this imbalance is exacerbated by the presence of peers, because peers activate the incentive processing system, which tips the balance further. So our first research into this was done under the auspices of a research network of the MacArthur Foundation that I directed on adolescent development and juvenile justice. And the study was designed to look at age differences in capacities that affect judgment and decision-making. The main purpose of this research was not to study risk-taking per se, but to understand how adolescents and adults differ in ways that might help us formulate smarter juvenile justice policy. But a lot of the things that are relevant to judgments about adolescents' criminal behavior are relevant more broadly to risk-taking. So the study involved 935 individuals from 5 different places around the United States, ranging in age from 10 to 30, and the sample was quite diverse socioeconomically and ethnically. Most importantly, the different age groups are matched on gender, ethnicity, socioeconomic status, and IQ. So to the extent that we see age differences in the capacities that we're measuring, they're not due to demographic differences between those age groups. And in this study, we assessed different aspects of reward processing, including sensation-seeking, sensitivity to reward, preference for immediate rewards, and then sensation-seeking behavior, so not just self-reports. And we also assessed cognitive control, self-reported impulse control, the extent to which people waited before acting on a task measuring that, self-reported anticipation of future consequences, and strategic planning. Now let me start by showing you some of our findings in the realm of reward processing. So if we start by looking at self-reported sensation-seeking, and this is a sample item from our scale, which is a subset of items from the Zuckerman sensation-seeking inventory, what we see is that self-reported sensation-seeking follows this upside-down U curve that I described before. This is very similar to what we see if we look at changes in dopamine activity in the brain, increasing from pre-adolescence into puberty, peaking sometime in early to mid-adolescence, and then declining as people age into adulthood. This is paralleled by answers to items that ask people to compare the benefits to the risks of various kinds of risky activities, like unprotected sex. These data show a composite risk preference measure that cuts across a number of different risk behaviors, like smoking, driving in a car with somebody who's been drinking, engaging in unprotected sex, and so on. What you see here is, again, this inverted U-shaped function increasing during the early part of adolescence, peaking in middle adolescence, and then declining. Now, in this study, we measure our various constructs using behavioral tasks administered on the computer, as well as self-report measures. And one of the tasks that we use to measure reward sensitivity is the Iowa gambling task. So in the Iowa gambling task, you're presented with 4 decks of cards, all turned face down. This is all on the computer. And you're told that 2 of the decks are good decks and 2 of the decks are bad decks. And each card, when flipped over, contains information about whether you've won or lost points. And in this program of research, we pay individuals to participate, but we also tell them that the better they perform, the more likely it is that we'll be able to give them a bonus payment. We don't define what better is, but we do motivate people to do their best on these tasks. In reality, we give everybody the bonus payment, but they don't know that when they're performing in the study. Now, we present these cards in 3 blocks of 40 trials, and we tell you that what we'd like you to do is to maximize the number of points you earn by choosing from the correct decks. And so it looks like this. You're presented with 4 decks, and then an arrow appears on the screen asking you if you'd like to play or pass from a particular deck. And if you agree to play that deck, the card flips over and you receive some information. And if you pass, the card stays in this presentation and you don't receive any information at all. So here the person chose to play from deck C, the card turned over, and the person sees that she's won 100 points. And we keep a running tally on the bottom of the screen. So what do we mean by bad decks and good decks? Well, the bad decks have larger gains so that when the cards are positive, they're very large numbers, but they also have very large losses. And the ratio of gains to loss is calibrated in advance so that if you keep pulling from the bad decks, you will lose points over time. However, many people find, and those of you there who like to gamble will resonate with this experience, it's like playing blackjack, knowing that the house is going to win the longer you stay at the table, but enjoying that rush that you get when you're dealt blackjack. And the bad decks in the Iowa Gambling Task create a similar kind of feeling. We can contrast these with the good decks, where there are small gains, but there are small losses. And they're calibrated so that if you pull from the good decks, you will gain points over time. And what we do when we administer the Iowa Gambling Task is we track people's card choices over the course of the 3 blocks of 40 trials. Now, because of our play versus pass option, we can separate out 2 very different behaviors. One is choosing the good decks, which is a measure of how much people are paying attention to rewards, versus avoiding bad decks, which is how much they're paying attention to costs. And when you separate out those 2 phenomena, you see something very interesting. Along the y-axis here is the absolute number of changes in card selection over the course of the task from the beginning block to the final block. And if you, the best way to read this figure is to start actually on the right and to look at the oldest age group where you see that the red bars, which represents attentiveness to the rewarding decks, and yellow bars, which represents avoidance of the bad decks, you see that in the older age groups, those bars are about equal in length. And that means that among the adults, they're paying just as much attention to moving toward the good decks as they are to moving away from the bad decks. Now if you shift your point of view to the left-hand side of the figure, and you see in the youngest age groups that the change over the course of the task is entirely in they're pulling more cards from the good decks, and very little change in the extent to which they've diminished their pulls from the bad decks. And if you just focus on those red bars, what you see now is this familiar pattern of an inverted U-shaped curve, consistent with what we saw in self-reported sensation-seeking, self-reported risk preference, and what we know about changes in dopamine activity in the brain during this time period. We also measure reward sensitivity using a task that's called delayed discounting or temporal discounting. This is a task that measures individuals' preference for immediate versus delayed rewards. And so we ask, would you rather have $200 today or $1,000 in 6 months? And then depending upon the person's answer to that question, we give them a new offer that either raises or lowers the lower figure. And we do that repeatedly until the subject reaches a point where the subjective value of the immediate reward is the same as the subjective value of the delayed reward. So if you said, I'd rather have $1,000 in 6 months to this first question, my next question to you would be, would you rather have $600 today or $1,000 in 6 months? And if you said $600 today, I would then lower that figure to $400 on the next one and do this until I got you to a point where it really didn't matter. And we repeat this with 9 different trials with varying immediate amounts and different time intervals as well. And it's generally accepted in the field that a lower amount that individuals are willing to accept for the immediate reward indicates a stronger need for short-term gratification, because the person is willing to take less in order to get it sooner. So what we show here is that in a delay discounting experiment that we did, that younger individuals have a much lower indifference point. So this is a graph showing the amount that they would accept today versus $1,000 1 year from now, and what you see is that the figure is much lower for younger individuals than for adolescents and young adults. So together, I think the data that we have on reward processing paints a picture of early adolescence as a time during which individuals are highly sensitive to reward and especially sensitive to immediate reward. And that's consistent with what we know about brain development. Let me turn now to some of our findings in the realm of cognitive control. So we start again with the most simple way to assess this, which is with a self-report measure of impulse control. This is from the Barrett Impulsiveness Scale. And what we see here is a linear increase in self-reported impulse control that runs through early adolescence, middle adolescence, and through the 20s. So unlike the pattern that we saw for sensation seeking or reward sensitivity, here we see a gradual, pretty much straight line that continues on into the decade of the 20s. And this is consistent with what we know about brain development in regions of the brain that support cognitive control. We measure this behaviorally as well using a task called the Tower of London. In the Tower of London, you're presented with 3 colored balls that you see there on the left of the screen. And there are 3 pegs or placeholders on the right side of the screen, one of which can hold 3 balls, one of which can hold 2, and one that can only hold 1. And what we do is we show you a goal configuration, and we ask you to move those balls onto the pegs and back and forth between the pegs to rearrange them to match the goal configuration using as few moves as possible. And again, remember, we've motivated people to perform the tasks well by telling them that they'll get a bonus if they do. Now, in the Tower of London that we use, the tasks increase in difficulty from some that are very easy and can be solved in 3 moves, and others that are much harder and that take 7 moves to solve. Now, one of the interesting outcome variables that we track here is how long people wait before making their first move. This is important because if you make an incorrect first move, you're going to have to undo it, and that's going to make your performance overall worse, since we're judging you on the basis of how few moves you need to solve the problems. And if you look here at the red bars, which is time to first move for the easiest problems, what you see is that there are very few age differences here. Everybody waits about 5 seconds while making a plan. But now if you look at the more difficult problems, the green bars, what you see is a dramatic increase in how long people wait before making their first move. And this increase is steady, and it goes on from the earliest age period well into the latest age period. So that for the older groups, they're taking at least twice as long before making their first move on an easy problem as they are on the most difficult problems. Whereas the youngest individuals are not taking any more time for the hard problems than they are for the easy problems before making their first move. And this is indicative, we think, of age differences in planning abilities more generally and in cognitive control. This difference in the timetables of the development of sensation seeking and impulse control is borne out in an analysis that we've done of data from a very large-scale sample of Americans. This is the children of the National Longitudinal Study of Youth. It's a representative American sample of more than 7,000 individuals. And if you look at the developmental patterns of sensation seeking and impulse control, you see that sensation seeking, represented here by the dotted line, follows this inverted U-shaped pattern, peaking at around 16 or 17, whereas impulse control follows this linear pattern that increases throughout adolescence and into early adulthood. That red arrow shows you where the gap is the greatest between sensation seeking and impulse control. Both of these measures have been standardized so we can compare them. And that period here, let's say around 15, 16 or so, is a period of the greatest maturational imbalance, and it's not coincidental that that's the period of time during which a lot of risk-taking peaks. So just to pause and summarize this part of the talk before moving on, that the incentive processing system undergoes important changes at puberty that lead to a temporary increase in reward seeking that peaks sometime in middle adolescence. But that this is going on against a backdrop of still maturing self-control. And that this makes mid-adolescence a time of heightened sensation seeking and heightened impulsivity or diminished impulse control. And this increases the individual's vulnerability to risk-taking. And that's seen in actuarial data across a wide range of risky and reckless behaviors. I don't have time to show you this data today, but we are replicating the study that you just saw in the field in 10 different countries, and we are finding the same pattern around the world in countries that are very different from the United States, such as Kenya or Colombia or Jordan or China, and in some that are more similar to the United States, like Sweden and Italy. Now I want to shift gears and talk about the impact of peers on risk-taking during adolescence. I mentioned earlier that one of our hypotheses is that the maturational imbalance between the incentive processing system and the cognitive control system is exacerbated when adolescents are with their peers because peers activate the incentive processing system. So we know actuarially that adolescent risk-taking usually occurs in groups. So most experimentation with alcohol and illicit drugs occurs with peers. The automobile crash data shows that the risk of a serious accident significantly increases with the presence of teen passengers in the car, but that this pattern is not seen when adults drive with passengers in the car. And that FBI data show that group crimes are relatively more likely to be committed by adolescents than by adults, whereas solo crimes are much more likely to be committed by adults than by adolescents. So we should think of risk-taking not only as a kind of inherently adolescent phenomenon, but as one that is a group phenomenon more often than not. One possible explanation for this, and one that wouldn't be very interesting, is that because adolescents spend so much time with their peers, that everything they do occurs more often when they're in groups. So we've tried to get at that at our lab by manipulating the presence of the peer group experimentally. So what we do is we have participants in our studies come to our lab and we ask them to bring two same-age, same-sex friends. And we do this with adolescents, college students, and adults who are older than 25. And then we randomly assign them to take a test battery like the one you just saw, either alone or with their friends watching. And we've done studies that do this as a between-subjects design and others that do it as a within-subjects design. When we first began this line of research, we would have friends in the same room in the peer condition and not in the room when the subject was tested alone. Because we wanted to move into brain imaging research, we needed to develop a paradigm to have friends watching but not in the same room, because we can't obviously squeeze them all into the fMRI magnet at the same time. And so we began doing the study with the peers not in the same room but in an adjacent room where they could see the target subject's performance on a computer monitor, and we would make the target subject aware of when the peers were watching and when they couldn't see. This also gave us the control over what the peers were able to say to the adolescents, so that they couldn't explicitly encourage decision-making. So all that the subject was aware of was that the peers were able to watch. The peers were not communicating with the subject. In the first study of this that Margot Gardner and I did, we compared performance on a driving game. And what we see here is that when adolescents and college students and adults perform the driving game by themselves, there were no differences in their crash rates. But simply having people watched by their peers changed their behavior on the driving task significantly for adolescents, where it doubled the times that they crashed. It's changed it significantly for undergraduates, where it increased the crash rate by about 50%, but it had no effect at all on the behavior of adults. We then decided to take this into the fMRI environment. Let me show you the game that we used in this study. All of you who drive probably have had the experience of needing to get someplace in a hurry and encountering a yellow light and making a decision about whether to try to run that light or not. And that's what this game mimics. And I know, speaking for myself and having given this talk before, that many of us, even adults, make the bad decision when we're in a big enough hurry. So your goal in this task is to complete the driving course through multiple intersections as quickly as possible. And there are three things that can happen when you approach a yellow light. You can stop at the intersection and the light turns red, and you wait there while the light cycles back around to green, and you lose some time off the clock. You can run the light successfully, in which case you don't lose any time at all, or you can run the light and crash, in which case you lose a lot of time, twice as much time as you lose if you brake at the intersection. So all the subjects are aware of what the possibilities are that can occur when they make their decision to either go through the light or not. And so what we see here in the fMRI context is very similar to what we saw in our behavioral study, where if you compare the red bars and the yellow bars, that is, compare people's driving when they're alone versus driving when their friends are watching them from an adjacent room, that the presence of friends increases risky decisions, that is, the number of intersections that individuals go through in adults, but in adolescents, excuse me, but it doesn't have this effect on college students or adults. And so crashing is much more frequent among the adolescent drivers when they know that their peers are watching them. So this replicates the Gardner and Steinberg study I showed you a moment ago. Perhaps more important is what we saw when we looked at patterns of brain activity. So this is showing the differences in the adolescents' brains when their friends were watching versus when they were alone. And you see in that yellow rectangle the highlighted area of importance here. That is where we see the main difference between the two conditions. These areas are part of the incentive processing system. This is the ventral striatum and the orbital frontal cortex. What we see is greater activity in those areas of the brain when adolescents are performing this task with their friends watching than when they're alone. If you compare the brain activity in the adult sample between the peer and the alone conditions, you don't see any differences in brain activity at all. So this is something that's limited to the adolescents in this study. We've wondered what the possible mechanisms are for the peer effect. Why should this happen? Remember that we've now ruled out the possibility that it's because adolescents simply do everything more in groups. We've ruled that out by using an experimental design that randomly assigns people either to do the task alone or with people watching. So it can't be due to that. We've ruled out the possibility that adolescents put explicit pressure on each other to take risks because we don't allow them to communicate with each other when they're in the fMRI studies or the behavioral studies that I haven't shown you where they're not in the same room. And one possibility, though, that has been raised is that maybe adolescents are just trying to impress or to please their friends. That is to say, even if their friends are not explicitly encouraging them to engage in risky behavior, maybe adolescents are doing it because they know what their friends would want them to do. So we tried to think about how we can get around this, and we thought, can we test this study or this study's hypotheses in a sample of adolescents that have trouble or are incapable of mentalizing about what their friends think of them or would wish them to do. And so we did the study with mice. This study is just about accepted for publication in developmental science. So as I mentioned before, all mammals, including mice, go through puberty, and we know exactly when mice are turning from children into juveniles, and we know when they're turning from juveniles into adults. So what we did was we raised mice in a triad. So we took a breed of mouse and we weaned the mice from their litters when they were young, and then we combined mice from different litters to grow up in cages together in triads. So basically we created these little 3 mice peer groups, and they grew up together, as I said. And then when half of the sample of mice reached the juvenile period, which is about 30 days or so, we tested them, and I'll tell you in a moment what that test is. But we tested half of those juvenile mice alone and half of those juvenile mice with their cage mates, the ones that they had grown up with. The other half of the sample we tested after they had become adults, which is after 60 days or so. And we tested half of the adults alone and half of them with the 2 cage mates that they had grown up with. So basically, we're doing the same experiment with mice that we did with humans. The test for the mice was slightly different, and it was to put them in a cage where they had unlimited access to alcohol to drink, and we measured how much alcohol they consumed. This is a breed of mouse that is known to enjoy drinking, and it's a breed of mouse that's used to study the impact of alcohol on development. So what we see here is that for the juvenile mice, there's a significant difference in how much time they spend drinking when they're by themselves versus in the cage with their cage mates. When they're in the cage with their cage mates, there are separate sippers, so the mice all have equal access to the alcohol. But if you look at the adult data, what you see is that there's no difference in the time spent drinking for the adult mice when they're by themselves versus when they're in the company of their cage mates. So this is similar to what we're seeing in human adolescence as well, which is that the presence of peers affects them during adolescence in ways that it does not affect the behavior of adults. So to summarize this and to wrap up the talk and leave some time for some questions, the heightened reward value of peers during adolescence increases adolescents' reward sensitivity. It activates the incentive processing system in ways that, that exacerbate that maturational imbalance I talked about before. And this creates a bigger gap between the incentive processing system and the cognitive control system, and this imbalance increases the chance of risky behavior. And we think that the impact of peers on reward sensitivity may be a hardwired feature of adolescence, since we see this in another species, and where we can't attribute this impact of peers onto explicit encouragement or even implicit encouragement. What does this research mean for policy and practice concerning adolescence? If risk-taking is an inherent feature of adolescence, what's the appropriate public health policy? So I think most people would agree that classroom-based health education has not had a significant effect on adolescent health behavior. Abstinence education, for example, is virtually ineffective. Driver's education is virtually ineffective. Drug and alcohol education is not very effective at all. And we spend even hundreds of millions of dollars every year on classroom efforts that don't seem to make much of a difference. And this may be because these efforts are premised on the idea that adolescents have poor information or make poor decisions. As I showed you in the early part of this talk, that simply isn't true. That's not the reason adolescents take more risks than adults. So it seems to me that we might think about public health interventions during adolescence by changing the context rather than trying to change the adolescent. Now, what do I mean by that? The most effective anti-smoking intervention ever done has been raising the price of cigarettes, which makes them less accessible to adolescents. And that has been the main change that has driven down the rates of teen smoking in this country and around the world. So that was accomplished not by telling adolescents that cigarettes are bad. They know that. Not by telling them that cigarettes can lead to lung cancer. They know that as well, but by simply making cigarettes harder for them to get. So we can think creatively about how we can change the context so that adolescents are less likely to put themselves in situations where they can engage in risk-taking. You probably know that the main time of day for adolescents to engage in sex is in the after-school hours, and the main place in which they have sex is in their own homes or in the homes of their partners. And we can intervene to minimize that by having better and more extensive after-school programming for people this age so that adolescents are not left alone and unsupervised during the after-school hours. That's another example of changing the context rather than trying to change the adolescent. I've been especially interested in the implications of this research for legal and social policy. So if adolescence is a time of heightened risk-taking, should they be held to the same standards of culpability as adults? Should we grant them the same privileges that we grant adults? What are the implications for medical decision-making and for what's called the mature minor doctrine, which allows adolescents to make some medical decisions without their parents present? I hope that has interested you more in this line of work. You can go to my website at Temple University, which is posted there at the bottom of this slide, and you can find the papers that report the findings from the various studies that I've presented. So I want to thank you all for your attention this afternoon, and I believe that you can ask questions, and our moderator can facilitate that.
Okay, so I guess we'll start our question and answer session now. So if you'd like to actually chat with us and be unmuted, you can press the hand icon on the control panel, and that'll let me know that you want to speak with us, and I'll let you know when you're unmuted and when you can ask your question. And otherwise, if you'd prefer to stay muted, you can type your question in the question box. So I noticed that during the presentation we had a few questions entered into the question box. Larry, are you able to open that?
Let me see.
Because a few of them are kind of long, so I just think it'd be better if you could also just look at them.
I don't see them. Maybe you can read them? I see them on my screen.
So we had one question from Lisa. She said, are you separating psychosocial maturity from frontal lobe development?
The question is whether we're separating psychosocial maturity from frontal lobe development. No. In fact, psychosocial maturity is governed in part by frontal lobe development in the sense that a lot of the aspects of psychosocial maturity that we're interested in are governed by connections between the frontal lobe and other brain systems. So things like risk assessment and evaluation or resistance to peer influence, we now understand as regulated by crosstalk and communication between subcortical and cortical regions. That's a very good question.
Okay, and then we had a question from Thomas Capo. He said, regarding the Kaufman study, looking for the point of indifference, it reminds him of Michel's marshmallow study, and he wants to know if anyone compared the time course of the point of indifference in kids who would eat the marshmallow right away versus those who would wait for 2.
Yeah, that's a really, really good question. I don't think that individuals have done the delay discounting work with people that young or in people that young who have gone through a delay of gratification task like the Michel marshmallow study. The studies of brain activity during a temporal discounting or delayed discounting task have revealed that behavior on that task is due in part to differences in brain regions that we know regulate delay of gratification. So we would expect that individuals, children who have trouble waiting for the extra marshmallow would also prefer immediate rewards if given that kind of a task.
Okay, and then Trina is asking, she's interested in getting a copy, I guess, of the slides from the presentation. So that's something that you and I can discuss afterwards, Larry, and I'll be sending everyone a follow-up email, and we'll provide whatever you're comfortable with providing.
Okay.
So does anyone else have any other questions? You can type them in the question box, or you can raise your hand, and I'll unmute you. Hey, someone raised their hand. Okay. So hi, Nancy, you're unmuted.
Hi, can you hear me?
Yes.
Okay, my question is, I was wondering if the risk-taking behavior, how much of it is in part explained in terms of a bit of a one-upmanship that kicks in when we're around others? A little bit of group polarization maybe or something? Has that been addressed?
Well, that certainly is a reasonable hypothesis. I don't think that would explain the mice behavior. Now,
Right.
Not specifically risk-taking behavior, but we think that may be a part of it, but not all of it. In some studies that I didn't have time to show you today, we have done the peer manipulation with reward processing tasks that don't involve any risk-taking. So we've done several studies in which we have administered that delay discounting task to individuals when they're being watched by their friends or alone. And what we've shown now in two different studies is that the presence of peers drives down individuals in difference points. So it increases the attractiveness of immediate rewards during adolescence. Now that doesn't have anything to do with risk-taking, so that is consistent with our hypothesis that what's going on is that the presence of peers does something to the way that adolescents process rewards. And that may be more important than whether they're deliberately trying to to impress their friends with their bravado.
Okay, thank you.
You're welcome.
Okay, let's see. Thomas Cabell had another question. He wanted to know if you're going to be presenting at NITOP again?
No, I'm sorry, I won't be. I'm doing a presentation at SRCD, the Society of Research in Child Development, in April, which is in Seattle, and I'll be doing a pre-conference presentation on how to teach about adolescent brain development.
Okay, and Ada, I saw that you had your hand raised, so I've unmuted you.
Hello, can you hear me?
Yep.
Yes, Dr. Steinberg. I'm having a question concerning having the children involved in after-school activities. Does the presence or non-presence of the parents, whether they be directly involved or indirectly involved with getting the children to and from those activities, have any factor involved in lessening or leveling out their risk-taking behavior?
That's a good question. I don't know studies that have looked specifically at whether parents are transporting the kids, but we have done some research, and there have been other studies as well, showing that when pre-adolescents and adolescents are in contact with their parents during the after-school hours. So, for instance, if their parents call them at home to check in with them or ask their kids to call them at work to check in with them, that does diminish their involvement in problem behavior. And so there may be ways for parents to monitor their kids from a distance, and also by making sure that their teenagers have a plan for how they're going to spend the afternoon hours, that may help. It's also important for parents who live in places where there aren't after-school activities to make sure that their adolescents are not spending time alone, unsupervised, with peers during that time period.